Today we'll look at the causes of circular motion. Just like any other acceleration, a net force is needed to produce a centripetal acceleration and the resulting circular motion. This net force is called the centripetal force. You could also think of it as the force that maintains circular motion. Just like we have in the past, we apply Newton's second law in a certain direction, what we call the centripetal direction. So the net force in the centripetal direction equals the mass times the acceleration in the centripetal direction. This is no different than looking at the net force in the x, y, or perpendicular direction as we've done before. Centripetal force is the sum of the forces that act radially, which means they act from the center of the circular path through the object. We are not introducing a new type of force. Let's take a look at how a couple different factors affect the force needed to maintain circular motion. So in this scenario, we've got an object moving at a speed of 15 meters per second with a radius of 30 meters, and it has a mass of 10 kilograms. First, let's see what happens if we double the speed. So you can see we have a net force of 75, and if I dial that up to 30, actually before we do that, let's make a prediction. How do you think it's going to affect the net force? Is it going to double it? Is it going to make it 150? Is it going to be squared? Is 2 squared, 4 times as much? Is it going to be 300? Let's see. You can see when we double the speed, we get a net force that's 4 times the original value. That's because the force is proportional to the speed squared. What effect do you think doubling the radius will have? You see it's 300 newtons, we're going to 30 meters. Would you expect to need more force or less force if the radius got larger? Let's see what happens. When we double the radius, you can see the force needed gets cut in half. The centripetal force and the radius are inversely proportional. The broader the curve, the less force needed to cause that object to change its state of motion. That's why, highway curves can be more gradual. They are more gradual because you need to take those at higher speeds versus curves, in your hometown, you have to slow down because they're a lot tighter. All right, lastly, let's see what happens if we double the mass. We have 150 newtons. So what do you think is going to happen if we double the mass? Just like with, well, I shouldn't say just like, doubling the radius caused the force to get cut in half. Doubling the mass will double the force needed to maintain circular motion because the centripetal force and the mass are directly proportional. Let's look at 3 examples. First is for a car going in a circle. What forces are acting on the car? There's the weight of the car, the normal force, and then the friction. Both the normal force and the weight act perpendicular to the direction of the motion, the normal force acting up, the weight acting down. Only the friction acts radially, or towards the center of the circular path. So the centripetal force is just the frictional force, and that equals the mass times the centripetal acceleration. We would use this equation to start with to solve whatever we were asked to solve for. Next, we'll look at a child on a swing. There's a tension up and a weight acting down. So the centripetal force will be the tension minus the weight. Lastly, we have a car at the top of a vertical loop. There's a normal force from the track and the weight of the car, both acting down towards the center. For all these centripetal force problems, we'll always treat positive as towards the center of the circular path. So the centripetal force will be the normal force plus the weight. Let's review the steps for solving problems. These are the same steps we used previously when we studied Newton's laws in dynamics. First thing to do is to draw a free body diagram. Second, we need to resolve any vectors that aren't perpendicular into perpendicular components. Third, we apply Newton's second law in the radial direction, or centripetal direction. Lastly, we can use the resulting equation to solve for the unknown. And remember, for all these problems, the positive direction is towards the center of the circular path. Let's take a look at a couple example problems. A 0.65 kilogram ball is attached to the end of a string. It is swung in a vertical circle of radius 0.5 meters. At the top of the circle, its velocity is 2.8 meters per second. What is the tension in the string? Our first step is to draw a free body diagram. In this situation, we've got the weight of the ball acting down, and we've got the tension also acting down. The second step would be to find or to resolve any vectors that aren't perpendicular into the components, but in this case we can skip that because that's not needed. Third step is apply Newton's second law. So we're looking at the forces that act in the centripetal direction, or radially, and they're going to equal mass times the centripetal acceleration. So our two forces acting in the radial direction are the weight and the tension, and they'll both be positive because they're going towards the center of the circular path. In this case, we're solving for tension, so we'll subtract the weight to get that equation. Now we can just plug in our numbers. We have 0.65 times 2.8 squared divided by 0.5 minus 0.65 times 9.8, which gives us 10.2 newtons minus 6.4 newtons, and a tension of 3.8 newtons. Our second problem is pretty much the same situation, except now the ball is at the bottom of its circular path. Again, we'll draw a free body diagram. Now we have the tension acting up and the weight acting down. No need to resolve any vectors into components, so we can skip to step 3, where we're going to apply Newton's second law in the radial direction. In this case, because tension is acting up, or rather tension is acting towards the center of the circular path, it's going to be positive, and we'll subtract the weight because it's acting away from the center of the circular path. So we have tension minus weight equals mass times centripetal acceleration. Again, we're trying to find the tension, so we're going to add the weight to the other side. Now we can plug in our numbers, and we have the same numbers as we had in the first example, except now instead of subtracting, we're adding. So we've got 10.2 plus 6.4 newtons, which gives us 16.6 newtons. We'll round to 2 sig figs, so we have a tension of 17 newtons. In our third example, we have a ball is attached to the end of a string. It is swung in a vertical circle of radius 0.75 meters. What is the minimum velocity the ball must have to make it around the circle? Now I can't demonstrate this here, but if you could imagine taking a ball on a string and swinging it in a vertical circle, the slower you go, in that point where the ball just barely makes it around the circular path, you notice that that string goes slack. So we can infer then at the minimum speed needed for that ball to get around, the tension is going to equal 0. So when we draw our free body diagram, the only force we're going to have acting is going to be the weight. Again, no components needed, so we can apply Newton's second law in the radial direction. Now the only force we have acting is the weight, and it's acting towards the center of the circular path, so we'll have weight equals mass times centripetal acceleration. We have mass on both sides, so we can cancel out the mass. Multiply both sides by r, so v squared equals g times r. And then if we take the square root, we get v equals the square root of g times r. We'll plug our numbers in. We got square root of 9.8 times 0.75, which gives us 2.7 meters per second, and that is the minimum speed needed for the ball to make it around the circular path. Any slower, and the ball would fall, the rope would go slack, and the ball would fall and not make it around.